Blindness caused by diabetes is defined as diabetic retinopathy. And let me tell you, this is a horrific disease. Just imagine seeing the world like this for the rest of your life and not being able to do anything about it. Over the next 3 decades, the number of Americans with this disease is en route to double to 14 million people. It's a race against the clock for researchers to discover therapies before vision loss becomes irreversible. Now, such therapies do not currently exist because diabetic retinopathy presents very specific landmarks seen in humans but is not seen in any current research models. Genetically modified rodents have been used to model the disease. However, these animals die before showing any early stage landmarks. Chemically induced models have also been popular. However, these animals die before showing any late stage landmarks. The world needs a rodent model that develops diabetic retinopathy as humans do. My team and I discovered that the Nile rat does exactly this. The way in which we made this discovery was by studying the eyes of 110 diabetic Nile rats. My team employed the gold standard for studying diabetic retinopathy with the use of the trypsin digest, which washes away neurons but leaves the snowflake-looking vasculature of the retina intact. Now, studying the vasculature is very important because it houses the most significant landmark of diabetic retinopathy, degenerated capillaries. My role in the project was to design a protocol which allowed us to quantify and categorize these degenerated capillaries. Their presence in the eye indicates a blockage of blood flow. If there's no way to deliver nutrients to the cells responsible for seeing, blindness will result. If you take a look at the data we compiled, you'll notice that the longer the duration of diabetes in the Nile rat, the larger the percentage with diabetic retinopathy. Now, this same exact correlation is seen in humans, thus ensuring that any novel therapies which treat the disease in the Nile rat also have a high likelihood of working in humans. This is big. Because of our discovery of this translatable model, we may now test our therapies to see if our therapies work on this translatable rodent. What is our therapy, you may ask, and what is our ultimate goal? We suggest safely injecting stem cells into the eyes of patients afflicted with diabetic retinopathy. These stem cells have a fate capable of not only rejuvenating the vasculature, but replenishing any lost cells in the eye. Now, let's think of a diseased retina as a fixer-upper home. Injecting stem cells remodels the home by adding new walls, floors, and pipes. I joined this ambitious project as a curious undergrad who questioned whether therapies would work in non-translatable rodents. My team and I reasoned that only by taking a step back towards finding the correct model could humanity make a leap forward in discovering a cure. Thank you.